right? So here is updating the beta prior. And recall that this is, again, our data is 12 successes out of 20 experiments. And the likelihood and the data is a function of the quantity of interest, okay? So again, we saw that last time. Here we're seeing this again, that because it's a binomial experiment, we can write out the PMF for binomial. So it's this n choose k, p to the power of k, 1 minus p to the power of n minus k, and keep in mind the range of k itself. But at the end of the day, we think of this as a function of the unknown parameter, right? So we know that later, once we observe our data, we know what k is. So k will be given. And then n is always given because that's the fixed number of trials that you're doing in the binomial experiment. So what's left for you is the unknown p. Okay? So likelihood is always a function of the unknown parameter. So keep that in mind. And earlier, we just did the beta prior for p, which is also making p as random. So now we have these two random things, and then trying to derive the posterior for p. Okay, so it's always a function of p itself. So, well, this is really short exercise here. The likelihood function, when you have n equals to 20 and k equals to 12, it will just become this likelihood function, 20 choose 12, p to the power of 12, and then 1 minus p to the power of 8. And you see that here, that's what I meant earlier, that we typically going to write LP, where L stands for likelihood, and then whatever goes into the parentheses is the unknown quantity. All right, so that's from before as well. And now we have a prior that is continuous. So how are we going to use Bayes' rule? So recall that for the discrete case in equation 15, we have this discrete case for the Bayes rule, right? And we wrote those functions to compute step by step, like the prior from the joint, and then the posterior at the joint, and then the posterior with the Bayesian crank function. For continuous p, we know that, well, the denominator probably doesn't work anymore because we don't have a finite number of p value, like the values of p that we're going to use. We actually have a continuous distribution for the p. So we cannot list each value of p anymore. We have to figure out a way to derive the posterior. So for now, let's keep in mind that, well, since it's continuous, we're not going to do summation anymore. We're going to do integration. Okay, and for now, for simplicity, what we're going to focus on is the product of the prior and the likelihood for now. Okay, so right now you see that in equation 16, we're using a proportional sign, indicating that the posterior distribution of p, given the data, is going to be proportional to the product of the prior and the likelihood. Okay. So for now, we're writing this way. We're going to figure out how to work with the denominator after we work with the most simple case for now. And if you're curious why we can ignore what's happening in the denominator, remember that once we have this, so essentially, the continuous case of this Bayes rule is replacing that sigma with integral, right? And the integral, actually, we're going to get rid of all of the subscripts of this p as well. What we end up having is what I circled here. I'm just going to write here for you as well, is that we are looking at the product of the prior and the likelihood, and then integrating over p. Okay? And we know that p is from 0 to 1. Right? Yeah, so that's what's happening in the denominator. And for now, maybe just a short exercise practice for you as well, that notice that the prior will still be pi p, that's fine. The likelihood, right now, we're writing it in terms of p, but we know that the likelihood can also be written as the data given the random variable, right? So that's what we saw before. So we use the binomial experiment and the binomial PMF to write about the likelihood. And because we focus on P itself, so write it in terms of LP, but it's also, we can always just write it as Y given P, right? So if you work out the math a little bit over here, you see that this is what? This is a marginal, right? and this is a conditional, right? So the product of these two is what? Is the joint. So I'm abusing notation a little bit over here. I'm just going to use y, f as a generic form, right? So from the product of the marginal and the conditional, I come to the joint, right? And then from the joint, if I integrate out one of this, I'm going to get the marginal of the other, right? So that's why, even though we don't even have plug in any kind of values of anything, we know that this will always be the marginal probability of y. So that's why I'm writing over here. So this is going to be fixed, because remember, in Bayesian thinking, we think that the data is fixed. Okay? So that's why this fy going to be fixed. So whatever goes in here in the denominator for the continuous case is going to be fixed. And that's why for now we don't worry about what it is. And that's why we can have a proportional sign and then focus on the product of the prior and the likelihood. Make sense? All right. So even if we don't care about fy for now, we still have to deal with the rest. And the rest might be new to some of you. So I'm just going to work it out in the particular setup that we have. So keep in mind, so question 17 is just carry over from previous slide. And the prior, we remember that we have this beta 3.06 and then 2.56. The likelihood, we know it's a binomial experiment. And we know that y actually in the end is going to be 12, because that's the data that we collected. So we need to derive this conditional distribution, which is the posterior p given y. So I'm going to write this out for you, that I'm expressing the entire PDF, in this case for the prior. That's from the beta distribution that we just covered. The likelihood we know, when y equals to 12, then it's going to be 20 choose 12, p to the power of 12, and then 1 minus p to the power of 8. So I'm asking you just to look at these forms a little bit, especially combining with equation 17, because we know that, well, the posterior are going to be proportional to the product of this two. Okay? So try to work that out a little bit. You might not see like the final answer directly, but at least right now, get to see what's so special about the prior distribution and the likelihood. They're both in a very, I would say, the same form. And then recognizing that can help us to come to the last point of how to get the posterior. I'm gonna pause here for a couple of minutes. And one more thing, I guess, is remember we care about, so we're putting a proportional sign here, right? So that means, and also on the left-hand side, notice that the data is being conditioned. Whatever is being conditioned is considered known. Right? So you don't have to worry about it, okay? And the only unknown is P. So that tells us, yes, in the prior, there are a bunch of, I would say just one constant over here, right? And then in the likelihood, the 20 choose 12 is also a constant. It's not, both of these terms are not dealing with P. So since I'm using a proportional sign here, those constants can go into the proportional sign as well. Okay? So that can help you simplify, I think, the problem a lot more. And you will see recursively throughout the semester that it's a technique that we do. Okay? So I'm going to break for 2 minutes and try to derive the posterior. Okay, let's look at this together. So what I was saying earlier is that because we're working with proportional sign, so those are considered constants, right? Because they're not about P. P is the only random variable here. So when we go to the posterior, we simply doing the proportional sign of the prior times the likelihood. And that is, well, if we express the whole thing, I put everything here for now. But then immediately you can throw away those constants into the proportional sign and only focus on the random part. And the random part is P to some power times 1 minus P to some power. And then again, P to some power, and then 1 minus P to some power. Right? And then we know that you can combine those powers. So if you drop the constant, you get to the second last line. And then if you combine the powers, you come to this point. Okay? So So notice that, again, maybe some of you are going to immediately ask, well, why don't you simplify the -1? So this, again, is because we're going to use this particular format to recognize that the posterior distribution is actually a beta distribution. Okay, so you can always get that -1 into this, so you're going to get 14.06 and 9.56. But in the end, we're trying to recognize what the posterior distribution is, and then leaving the -1, -1 there will be helpful. So that's why in equation 18, I left it there, at least for now. So we know that the posterior are going to be proportional to this, and that's what we have at this stage, which means that this is actually going to be another beta distribution. And in particular, remember the, so this earlier, this is from the prior, but we can see that this is what the PDF of the beta going to look like, right? It's going to be 1 over the beta function of the two shape parameters, and then the random variable to the first shape parameter -1, and then 1 minus the random variable to the second shape parameter -1. So we know that this is the form of what a beta distribution will look like. So if we focus on that, don't worry about the constants for now, but if we focus on that, we know that this should be the first shape parameter, and this should be the second shape parameter. And then we come to the point that's going to be a beta 15.06 and then 10.56. So, like I said, this is the simplified version for now, and I just want us to focus on the random part and not too much worry about the constants. But after we cover this, I will go over the detail of how, if we're not going to use the proportional sign, if we keep everything, all of the constants together, in fact, we can still come to the point that it's going to be a beta distribution. Okay? But the technique that we're doing right now, like, don't worry about the constants, you will see a lot of times throughout the semester, because what matters is the unknown, and then whatever else is a constant, and then that can always go to the proportional sign. Okay. Questions here? All right. If not, to summarize, this is what we typically have. Generically, if you have a prior for B is beta AB, and then if your sampling density, so this is a new term here, we call it sampling density because that's how the data model is. It's sampling for the data. Okay? But immediately we're going to move this to a likelihood, right? Like what we usually do. But here, we're still going to write the sampling density in terms of Y, and then it's binomial NP, generically N number of trials, and then P success probability. Then we can see that the posterior distribution is going to be A plus Y, and then B plus N minus Y for the two shape parameters. What we worked on just now for the derivation is for the specific case with A and B, and then also N and Y that we know, but this is the generic results. Okay, I left this as one of the homework problem for you to derive this generic results to make sure that you know why this is the case. But for now, this is just a generalization of what I just did. And now we finally come to this table, because earlier we were talking about the different choices of the beta prior distributions. So one thing you notice that is you start with the prior, which is beta, and then you arrive at the posterior distribution, which is another beta. Okay? So when the prior distribution and the posterior distribution, they come from the same family, we call this conjugate prior. This is an important term, and this is the first conjugate prior we saw. So conjugate priors is when the prior and the posterior distribution of the unknown parameter, when they come from the same family of distribution, it's conjugate. Okay? So in this case, we start from a beta prior, and then we end with the beta posterior. In this table, I'm listing, so by each row, we're talking about the prior, and then the data likelihood, and then the posterior. So these are the 3 steps that we emphasize about Bayesian inference. On the columns, we're looking at success and failures. So this, on the second row, the data and likelihood, that's just what the data is, right? y is the number of successes, and n minus 1 is the number of failures. So these are coming from the data. And the A and B here, we put it in the row for prior, and this is just a way to think about, just corresponding to the earlier discussion about beta 4.2 and beta 2.4. So we typically also think about A as the prior success numbers and B as the prior failure numbers. So you can think of them counts. Okay, and because it's conjugate, you will see that once you go to the posterior, the two shape parameters A plus y and then B plus n minus y, they are the posterior counts of successes and posterior counts of failure. So this table gives you like a step-by-step update for the posterior, but I think it's more important to know exactly how the update was done, just not when we're doing the derivation. So this is, a shortcut if you want to memorize things, but it's really just because of the derivation that we did that we know that we start with the beta AB and we end with beta A plus y and B plus n minus y. Make sense? Yeah. So obviously we come to a known distribution. Well, we don't know beta well enough for now, but we know that it is a beta distribution for the posterior. So that means if I want to make any inference about the posterior, I can make it based on the beta distribution, right? So this is good. Why we care about conjugate priors, because they're simple to work with. You come to an analytical solution that you know exactly what the posterior distribution will be. Later in the semester, we're going to see cases that, well, unfortunately, we cannot derive the posterior to a known distribution. Conjugate priors might not work. Okay? So those will be the cases that the computation techniques are important. Right now, we know for sure it is a beta, so we can summarize, like, say, the mean, the variance, all that, just based on what we know about A, Y, B, N. But then later in the semester, you will see cases that conjugate priors do not exist, or even if they do, you have multiple parameters in the model that you have to come up with multiple whatever that is needed for each of the parameters. And then that will be much more involved in terms of the computation. All right, so if you want to know how to do it in R, just some sample script here. So we know that the posterior is beta A plus y, B plus n minus y. So, and then with the particular A values of A, B, and then y and n, that's what I put in here, the first two rows. And then you can come up with the AB mu, which is just the sum of these two, just like we're replicating the table that we just saw. You're adding up the two rows. Then you know that, well, the posterior distribution, which is the beta with these two shape parameters, and that's what we just derived earlier. Okay? And of course, if you want to plot them, you can plot the posterior and prior on the same plot, which is typically done because we want to see, well, you start with a prior belief, and now you add the data into your inference, and then we can see how different the data is driving the inference for the posterior. So we did it once, I think, maybe last week then, that we're looking at the all-nighters example that we collect the data and then we plot the prior and the posterior. So back then they're discrete, right? So we're plotting dots, okay, particular values. Here, both of them are continuous because we know that beta are continuous distributions. So for you, I want you to discuss two things with your neighbor. One is compare prior mean and the posterior mean. So these two numbers, I give it to you, 0.544 is the prior mean for the beta distribution. And then the posterior mean is 0.588. So compare this and recall that the sample mean is 0.6 because we get 12 successes out of 20 trials, right? So compare that, let us know what you think. And also, very importantly, in exercise 2, compare the spreads of the two curves. So when we say spread, is really just talking about the range of the P on the x-axis that is being covered. Okay? So think about those two. One is about the mean, the other is about the variance. Essentially, I'm trying to encourage you to think about the changes and the differences and similarities, I guess, also between the posterior and the prior in terms of its mean and its variance. And what does that tell us about the process of the Bayesian inference, how Bayesian inference is helping us to sharpen and update our belief. So I'm gonna pause here for a couple of minutes. Okay. Yeah. Anyone wants to offer any ideas about either of the exercises? If you compare the mean, what do you find? And if you compare the spreads with the variance, what do you find? Tom?
So the mean will become closer to plus after the data. As you see, it's moving from 0.5 or 0.58.
Great. So you start with the prior mean, which is 0.54. And you know that the sample mean is 0.6, and you can see that posterior is somewhere in between. Okay. In a minute, we're just going to do a little exercise as well, as to see how the posterior mean is actually a weighted average between the prior mean and the sample mean. So we're going to see that in a minute. But right now, the importance is that yes, it's going to be somewhere in between. And what about exercise 2? What do you think the two variances are telling us, Josh?
The variability has decreased, and it kind of tells that whenever you see data, that kind of reinforces our belief, and that contributes to decrease the variability.
Yeah, so just on this plot, you can see that the prior, well, for P goes from 0 to 1. And then the posterior is much more concentrated with a smaller spread. So that tells us the Bayesian inference in general, as well as just the data itself, helps us to update and also sharpen our belief. So that's why we use the word sharpen, because the less or the smaller the spread, the more concentrated, the less uncertainty you're going to have when you're making any inference, and that can be seen for this particular plot of prior and posterior. Okay. Yes.
Is like beta 5.3 the same shape as beta 10.6, or would one be sharper?
What do you think? What do you all think? So Aiden's question is beta 5.3, and then beta 10.6. So I guess one thing special about this 2, or any kind of multiples of 5 and 3, is that the ratio of the prior success. So let's just focus on prior for now. It's both of them the prior. Then the ratio of the success over the failure in terms of the prior distribution is the same, right? It's always 5 versus 3. Is there any difference between these two? What do you think the difference will be?
I'm just guessing, but I think the 10.6 one would be sharper since we have more data points. I'm not sure.
Okay, so we need to be careful when we're talking about things. So first of all, right now we're talking about the prior, right? So it's not about the data itself, but indeed we're talking about using data, especially the two shape parameters, to represent our strength. Like, okay, I should say A, which is 5 in this case, is the prior number of success, right? And then 3 is the prior number of failures. And then if we move to beta 10.6, then we double that size, right? So size, just like data size itself, even though it's in the prior, it's going to still make a contribution into the posterior in the end. So one thing good to know, which I was about to mention later anyway, but the AB, so we know that we use beta AB. And A is the prior success number, B is the prior failure number, but the sum of A and B, we actually use this to represent what we call the prior sample size. In a sense, in next slide, when we get to the point that we're going to derive why the posterior mean is a weighted average between the prior mean and the sample mean, you're going to see that the sum of the A and B is going to play a role in that. And in short, yeah, so in this case, the sum of this 2 is 8, whereas in sum of this 2 is 16. So in terms of prior, is 2 times in terms of the size, right? And then the sum of the A and B, not only we call it as the prior sample size, and the value of it is telling us the strength of our belief. Okay? So if it's larger, means that, well, even though I have the same 5-to-3 ratio, I have stronger belief in this prior. If it's going to be smaller, I'm going to have weaker belief in terms of prior. Okay, does that answer the question?
Yeah.
And related to this, let's now just move to the point that I do want to spend the time to discuss how we can see that the posterior mean is a weighted average of the prior mean and the sample mean. So remember, the prior is AB, and then the mean of that beta distribution. So this is just a known knowledge that if you have prior of beta, AB, then the average, this is property of beta, I think, which is, what is it again? It should just be A over, I think, A plus B. And then what the,
Is that like an E or like
oh,
an
sorry,
I?
yeah.
Sorry.
No, it's expectation, sorry.
Oh, okay.
Yeah. And I guess also because of that, let me just move things down a little more. Beta. AB. So if you have your prior to be this, then the expectation of the random variable will be A over AB, A plus B, sorry. So that means we also know that just now, the posterior is what? Beta A plus Y, right? And then B plus N minus Y. So following the same formula for the mean, we know that the posterior mean will be the new A, which is A plus Y on the top, divided by the sum of these two, which will just become the negative one, positive Y gonna be canceled. So it's gonna be A plus B plus N. Okay, so this is the prior mean, and this is the posterior mean. And I should mention that the sample mean in this case will just be 1 over N, right? So prior mean, posterior mean, and sample mean. Let's spend some time, just work it out, algebra a little bit, to see how you can show that the posterior mean, we call it a weighted average. So it's gonna be the prior mean times some weight plus the sample mean times some other weight. And of course, the two question marks, they're gonna add up to 1. Okay. So spend some time, might be a little bit creative. You have to think a little bit more creatively of how we can show that. So the goal here is trying to show that we are able to prove that the posterior mean is weighted average of the prior mean and the sample mean, and that can shed more light of how the Bayesian inference is being done. So I should say the right hand and the left hand side is A plus Y over A plus B plus N. So what are the two question marks should be? If you figure it out, think about why earlier I was talking about the sum of A and B as the prior sample size. Also tells us about the strength of your prior. Okay, so this is open-ended, take some time, work it through. Yeah.
And should they be different things for X? With the with the question mark.
Yeah,
Those are-
sorry, yeah, so this are multiplication, sorry. And the question mark, yeah, so these are the two things I want you to come up with. They're gonna be different. They're gonna add up to 1.
Okay.
That's a quick hint. So you see that on the left-hand side, the denominator has this 1, right? Yeah, so this actually giving us, I think, a hint that both of these weights that we're talking about will be able to help us to create this A plus B plus N in the denominator, right? So if I have A plus N here for this term, you still have to figure out what's in the numerator, and here will be a plus b plus n, right? So then, well, the goal is that we're gonna try to cancel the terms of a plus b here, right? And then the n here. So, well, since I'm already here, I'm just gonna say it. Yeah, it's all right. So a plus b, a over a plus b times a plus b over a plus b plus n plus y over n times n over a plus b plus n, right? So then that can help me cancel out those two terms. And then we're left with, well, once you simplify it, it's gonna be the left-hand side. Okay. So what this tells us is that we are having this prior mean multiplied with the weight, right? This is sample mean multiplied with the weight. And notice that the weights add up to 1, and that's what we call them weights. Okay, they add up to 1. And more specifically, if we just focus on this one for now, what this is telling us. We talked about a plus b as the prior sample size, right? And n is the sample size of the data. So what we're doing is we're looking at the ratio of the prior sample size over the data sample size. And then similarly, this term is the data, the data sample, prior plus data sample size. Sorry about it. Because it's the sum of them, right? Oh, can't see, sorry, thank you. Let me see, eraser. Keep forgetting about the blocking. Okay, let me write it over here. So a plus b over a plus b plus n is the prior sample size. I'm going to use SS. And then down here is the prior sample size plus the data sample size, right? Because a plus b is the prior sample size, b is the data sample size, so we add them up together. And similarly, you can have that, this term, n over a plus b plus n will be the data sample size over the sum of these two. And I'm hoping that this can convince you even more about why earlier we were talking about if you're comparing theta 5,3 versus theta 10,6. So we already know that the ratio of the success and failure is the same, right? 5 to 3. But then the sum of them, one is 8. The other one, one is 8. The other one is 16. So we double the size, right? And if you imagine that we're working with the same data, which is n, right? If you already have the same data, then this ratio, the two ratio, are going to be changed based on the sum of a and b, right? And obviously, especially if you think about this one, the ratio here, that the larger the a plus b, the larger this ratio, which means that the prior is going to give a stronger or like a bigger influence in terms of the prior. Sorry, in terms of the posterior for the mean. So the prior is going to have a bigger influence simply by increasing a plus b. Okay? So also similarly, if I'm going to fix a plus b, like I'm just going to go with the same prior regardless, then the data, if you're going to have a larger sample size, then this term is going to be bigger, right? And then that also tells us that, well, the larger the sample size from the data, the stronger its impact going to have on the posterior. So we also know from the beginning that the posterior are going to be some kind of summary or the sum of the prior and the posterior, and in this the prior and the data, sorry, and hopefully in this case with the beta binomial case that you can see more clearly that prior sample size, why we care about it, and then the data sample size, obviously, and then how they together is contributing to the final posterior. The variance is much more complicated to show the results, so don't worry about it. At this moment, especially link this to the previous plot that we just saw, the exercise 1, that we're really seeing prior mean, sample mean, and then this will be a weighted average. Okay? The exact computation obviously going to depend on what is A, what is B, what is N, and what is Y. Okay? But for this case, at least get the idea why that is working. And for exercise 2, earlier we were talking about, well, it's about the variance. It's going to be much more complicated to show, so don't worry about it. But the key message here is that when you are doing Bayesian inference, the data are going to help you to sharpen and update your belief. In terms of spread or the variance, it's showing the way that you're going to have a smaller spread, meaning less uncertainty. Okay. All right, I have 5 minutes left. I don't think I will be able to finish what I need to talk about, but just to set this up so we can continue from Tuesday when we come back, is just now we were doing the derivation of the posterior, thinking about everything else as a constant, so we never worry about what goes into the proportional sign, right? So the last part of this unit, like this section here, is to actually formally derive that if I have a beta AB for the prior, and then if I have my sampling density is a binomial, NP, then how can I formally prove that my posterior is a beta A plus Y, and then B plus N minus Y. Okay. I'm going to set this up for you. So maybe if you have time over the weekend, you can work on this. And then on Tuesday, we're going to come back to go through the detail. So to set this up, we know that the prior density will be 1 over the beta function AB, p to the power of A, 1 minus p to the power of, A minus 1, and then b minus 1, right? Here, the likelihood is n choose y, p to the power of y, 1 minus p to the power of n minus y, okay? So now we keep every constant, okay? We never throw things in the proportional sign. And the goal is to show that indeed we're going to come to a posterior distribution, which is the beta, and it's this particular beta. So to set this up for you, you're trying to prove or show what this is. So we're going to have a super long here that we're going to do a step-by-step that we have the prior times the likelihood. And earlier we were saying that the denominator for the continuous case will just be an integral, right? Integrating over the unknown parameter. So what this tells us, no longer here, that 1 over b ab e to the power of a minus 1, 1 to the power of 1 minus b minus 1, and then the choose function, we're just multiplying things together. Okay? Keeping all the constants. Do not delete them. Down here, a bunch of repeat, but important to keep them for now. Okay. So what we need to do when we come back is to show that, okay, so first of all, there are some simple things we can do. That even though we say that we don't throw constants into the proportional sign, but right now when we keep all of the constants, we can still see that they can be canceled out from the denominator and the numerator. So those two goes away, right? So you come to the point that you have, so hopefully you can see this, ba plus y minus 1, and 1 minus b plus n minus y, that's in the denominator. In the numerator, you will have the integral of the same thing. Okay. So obviously how we can proceed, and that's what we're gonna pick up from Tuesday. My hint for you is that stare at this denominator a little bit more. We know that in the end, it's gonna be a beta distribution, right? We even know what it is. It's gonna be this. It's very close already, right? You can see that the powers are working. We just need to figure out what does this integrate to. My only hint for you for now is that remember at the beginning when we introduced this beta distribution, I was saying that beta distribution is a proper distribution because it's going to integrate to 1. Okay. So how can I simplify this? What do I need to integrate this out to be something that I need? Okay. So that's my hint for you. And we're going to break today. And make sure that you bring your homework to the front. And I would say on Tuesday, bring your laptop so we can do some in-class exercise. I will remind you all of your email.